In the last section, we learned what it means to be a linear transformation. Namely, that is a map from Rn to Rm that takes some x and maps it to Lx. In this section, what we're going to do is, for those special transformations that can be seen as a matrix, we'll actually say what they are. Okay, now a canonical basis for Rn is this particular set, where Ej is the jth column of the n by n identity matrix. So, for instance, let's not use E1, let's use E2. That's going to be 0, 1, 0, down to 0, where there are n entries here, because that's in Rn. And notice I have a 1 in the second place. So there are indeed n of these, and you can see that's from the n by n identity matrix. Okay. As I like to say here, this comes out of left field. I'm just going to use this terminology because it's a bad habit, and I just want you all to be involved with my bad habits. So, okay. To determine the action of a linear transformation from Rn to Rm, we're calling it L, we consider its action on the canonical basis of Rn. The actions of L applied to each one of these elements in a canonical basis give rise to these j vectors. We therefore identify L with this particular matrix, which, since each Lij is with some yj, I can write like that. That makes perfect sense, doesn't it? Huh? Alright, let's talk about this. This canonical basis that I reference, this E1 hat up to En hat, the columns of the n by n identity matrix, they turn out to completely characterize how a transformation actually operates. So in other words, if I can describe how L treats each of our principal directions in n-dimensional space, oops, that should be M, because that's Rm. Oh, wait, no, I was right. Sorry, Rn. If I can describe how L acts on each of these n vectors, then I can completely describe a matrix that will have that same action, so that I can do something like Ax, rather than doing L applied to X. Okay, let's actually do this. Slide, let me remind you, I write down what L does to each one of these basis vectors, and that's the result, each one of these. So let's suppose L acts on E1 by producing this vector, and L acts on E2 by producing that vector. What I wanted to do is determine L's action on an arbitrary vector. Alright, so by this first statement, LE1 equals 2, 3, notice I can decompose this as 2E1 plus 3E2. In a similar way, I can say L applied to E2 is negative 5E1 plus 7E2. So then, if I'm trying to determine L of x1, x2, well, x1 and x2 are x1, E1, I'll use a hat here, plus x2, E2 hat. By linearity, this is x1, L, E1 hat, plus x2, L, E2 hat. I know what L does to both E1 and E2. And you're already seeing here in this particular decomposition that if I can say what L does to my E's, I can see what it does to an arbitrary vector. This statement here, I think, completely spells that out for you. But let me just elaborate further. So LE1 is equal to that. So I have x1 is equals x1 times 2E1 plus 3E2 plus x2 times what L does to E2, which is negative 5E1 plus 7E2. Writing this all out, I get x1 2e1, so that's 2x1 minus 5x2, and then 3x1 plus 7x2 as my final vector. If this step is too big of a jump, distribute these, write down what e1 and e2 are, and multiply by the scalar 2x1 and 3x1 and so on, and then combine those two vectors to get this. And if you're still having trouble with that, let me know and I'll help you out. Okay, now look at this. How can I see this last expression as a matrix product? Well, that's nothing more than 2, 3, negative 5, 7 applied to x1, x2. This is like a times some x, right? It's like the weights in the... Well, I could have actually done it from here. It's like the weights along with the columns. So, let's look at that. This is pretty trivial when you actually stop and think about it. What did L do to E1? It turns into 2, 3. That became my first column. What's L do to E2? Does that. That becomes my second column. So, just like in the previous, and that is the matrix for my linear transformation. It is really that easy. You simply write in what those are here. Now, as a foreshadowing, this is completely dependent upon this particular choice of a basis, whatever a basis is. So my choice of E1 and E2. We're going to find out that if we don't like E1 and E2 and we happen to like Bob and Mary, then this is not going to be the same thing. That's going to be a whole series of discussions. I don't know if y'all can hear that, but it is pouring here. It's like 2 inches of rain. It's terrifying. I'm actually scared for my life. But I think I'll make it. Okay, back to math. A theorem out of Now, the phrasing here, out of is me actually saying the slide. Let's make a theorem out of it. Alright, anyways. Suppose we have linear transformation. Alright, we've been talking about those a lot. Then there exists a unique matrix A such that A's action is the same as L's action. And what is that particular matrix? It's the exact one I spelled out earlier. Not shocking at all, given the last slide. It's that this is all finite dimensional, hint hint. Alright, now that I know that I can take a linear transformation and write it as a matrix, given certain cases, no. What is the matrix induced by homothety? So remember, a homothety takes some arbitrary vector x and maps it to lambda x. Alright, in this case, let's say we're working over R3. So we're going to take map from R3 to R3, call it capital H for homothety, and we're going to take some x, homothety, h sub lambda, and goes to lambda x. Alright, so what's it going to do? Then the matrix h sub lambda, well, what's h sub lambda do to E1? Well, E1 is going to go to lambda 0, 0. Right? Just by this right here. So that's lambda 0, 0. What's lambda with its action on E2? Well, it's 0, lambda 0. So that's 0, lambda 0. And then finally, what's the action for E3? Well, it's 0, 0, lambda. And so what we actually see here is it's lambdas on diagonal and zeros elsewhere. If you're clever about this, you can see that lambda is a constant multiple. So I can pull lambda out of the matrix, and it's 1, 0, 0, 0, 1, 0, 0, 0, 1. Well, by Jove, what is that? That is the identity matrix. So homothety is nothing more than a constant multiple of the identity matrix. This turns out, believe it or not, to be important even in very, very advanced mathematics. These are called scalar matrices. They have a very important property that you might learn if you major in mathematics. Foreshadowing for like 4 years from now. All right. Determine the matrix induced by counterclockwise rotation by theta. Ooh, now this looks juicy. So let's see here. We first look at E1 hat. That's going to have length 1. Now if we rotate this by theta, angle there's theta, we get a new point here. What are the coordinates of that point? Well, think about it. This is unit length, that's a right triangle, so the cosine of theta is adjacent over hypotenuse, which is 1, so that means that's the x. And then the sine of theta is opposite over hypotenuse, so that's the y value. So what does, let's call this rotation r sub theta, do to E1 hat? Well, it sends it to cosine theta, sine theta. All right, let's look at E2 now. Now, I'm saying E2 and E2 hat and E1 and E1 hat interchangeably. I mean the same thing for all of this. I'm not trying to confuse you, even though it probably is confusing. All right, so I'm rotating this vector here by theta clockwise again. So, whoop, like that. That again makes a right triangle. Now be careful here. The sine of theta is opposite over hypotenuse. This still has length 1. So that means this side right here will have magnitude sine theta, but because it's in the second quadrant, this point here, the first part of it, will be negative sine theta. Just using that over here. And then the cosine of theta is adjacent over hypotenuse. So that means the height here will be the cosine. Therefore, a rotation by theta applied to E2 hat will give me negative sine theta cosine theta. Therefore, the matrix of rotation by theta is going to be cosine theta, negative sine theta, sine theta, cosine theta. Now, interesting thing you can do to check this particular matrix is, remember last section we figured out what rotation by pi over 2 is. If you plug in pi over 2 here, what do you get? You get 0, 1, negative 1, and 0. So let me write that out. So r of pi over 2 is 0, 1, negative 1, 0, which is exactly what we saw last section. All right, now we're getting into some really hefty stuff. A function f is said to be onto, I will use the terminology surjective, if for every y in y there is an x in x such that f of x equals y. All right, let's do the lima beams. There's x, there's y, and f is our map between them. Okay? So I'm saying this particular map f here is surjective if no matter what value I pick over here, I can find something over here that actually mapped to it. So in other words, using fancy terminology, the codomain of f is the same thing as its image. Or I can write this to say f of x equals capital Y. So these are both capital X's. So that's a nice way of writing it. So for any y I pick, there's some x that maps to it. Next up, a function f is 1 to 1, I'll use the terminology injective if for every y in y, there's at most one x that maps to it. All right, let's get out lima beans again. Here's x, here's y, and here's big bad F. So if I take anything over here and look what mapped to it, there could only be one element that did this. Okay? Now, another way you can view this, and this is typically how people will view it, is if I have any two points over here, then they had to map from the same point. So in other words, if these are equal, then the things that map to them had to be equal. All right. Let's do a lot of examples. Actually, I don't want to do lima beans. I want to do lines because I'm going to show you this with real functions. All right, so let's look at x maps to x squared. So I have the real line over here, and I have the real line over here. This is my domain, this is my codomain. Now, the domain is all of this. What is the image of f? So if I did f to every single real number, what would I get? Well, the smallest such real number I'd get would be 0, and then I'd get every positive real afterwards. Well, by this token, what's that mean? Can this be surjective? Well, no, it is not surjective. Why not? Because in order for a function f to be surjective, if I pick any y value from over here, so namely that one right there, I should be able to find some x that mapped to it. Well, is there some x that mapped to this bad boy right here? Let's say that one's -1. Well, if that was the case, then that would be a value of x such that f of x equals -1. But what's f of x? F of x is x squared. So that'd be a value of x that squares -1. That's bad news bears right there. So it is not surjective. All right, the next question I want to ask you, is the function injective? Again, no, it's not, because this bad boy here, say it's 4. How many x values mapped to 4? Well, exactly 2. Namely 2 and -2 both mapped to 4, didn't they? And so it is not injective. All right, let's change this ever so subtly. Let's say we're going from 0 to infinity to 0 to infinity via f, but using the same rule. Okay, so this is me using advanced function terminology. A function is more than a rule. A function is a rule, like this, along with a domain and a codomain. These things matter. All right, so if I want to draw this out, I have this basically. All right, now what you ask yourself, is this thing surjective? Do I hit every single value over here in my codomain? Yes, I do, because they're all non-negative now, because of my stipulation here. How about injective? Well, do I have a double mapping? So if I pick any number here, so any, let's say it's a p, that's a non-negative real number, how many x values will map to it? Well, it's going to be x squared equals p. Well, we know the solution to that is plus or minus the square root of p. Now, does the negative square root of p fall inside here, assuming, of course, p is non-zero? Well, no, it doesn't. And therefore, this thing is injective. Now, to see injective in another way, actually using the definition to prove it, let's do that. So proof that f is injective. Now, in order to prove that, I need to show that if f of x1 equals f of x2, that implies x1 equals x2. All right, so what I do is I apply f to x1 and x2. Well, that's nothing more than x1 squared equals x2 squared. Now, if I take the square root of each side, I will get the absolute value of x1 equals the absolute value of x2. But think about x1 and x2. x1 and x2 are both positive or non-negative real numbers, so the absolute value of each of these quantities is just itself. So what I've done here is shown that f of x1 equals f of x2 implies x1 equals x2. Now, if you're really thinking about this step right here is the big step that allowed me to make the assertion that we're injective. In the previous example, that failed. Why did that fail? Because I couldn't say definitively the absolute value of x1 was just x1. It could have been negative x1 because I had negative real numbers at my disposal. All right. Now consider the same rule, but going from r to 0 to infinity. I want you to stop and think, is this thing injective? And is this thing surjective? All right, I'll pause here and let you think about that. All right. It is not going to be injective, but it will be surjective. Now, I have a nice way of explaining each of these to you geometrically, especially in the case when we're working in the plane. All right, so let's say you have your function f and you graph it. If you're going to be injective, which remember that's another way of saying one-to-one, you have to pass the horizontal line test. You know this from Algebra 2. So if I can draw a horizontal line, think about this. This horizontal line hit the graph twice. So in other words, here's an x1 and here's an x2. F of x1 equals f of x2, doesn't it? Because of the same y value. But does x1 equal x2? No, it does not. That's why this thing is not injective. On that same way, surjectivity. Surjectivity is about us being able to hit every single y value. Well, if I take my graph here and imagine that I project it onto the y-axis, I will actually completely cover the y-axis, won't I? Therefore, it is surjective. Now, you need to be careful with the surjective business whenever you have, say, that. Because you can't really use a graph like I did here. The graph here, there's the x-axis. The y-axis actually looks like that because we don't have the negative real numbers. And so the graph would look like this. And you can see here now, doesn't pass the horizontal line test, therefore it's not injective. And surjectivity, if I take my red graph here and I smush it onto my codomain, I hit every single value. And you can see, yep, sure enough, it is surjective. All right, I have a bunch of questions for you here. I want you to ponder these, and we will discuss these in class. Boy, these would be excellent test problems. Gosh. Oh, man. Man, these would be good test problems. Oops. Okay. Now, how does this abstract nonsense tie back to matrices and even echelon forms? Okay, let's see that. Let's consider the matrix A here. Note the transformation corresponds to A, corresponding to A is surjective but not injective. Now, how can we see that? It turns out that's pretty easy. Let's do surjectivity first. All right, so let's say I have the transformation I'm going to write as L, and I want to know if Lx equals y. So given y, there exists an x where this is true. All right, well, think what that is. This is us going back and saying, wait, hold up. Ax equals b, right? Because L is equivalently a matrix A in this case, and I am fixing some value b. So I'm saying, give me a b. Is there an x such that Ax equals b? Well, if you turn back to your diamond-crusted first page of your notebook, you'll notice that this is one of the conditions on the inverse function theorem. Now, looking at this, do the columns of A span R3? Well, yeah, they do, because I have a pivot here, and a pivot there. So yes, it is surjective. Now, is it injective? Okay, let's think about that. In order to prove it's injective, I need to know if Ax1 equals Ax2, does that imply x1 equals x2? Well, I'm going to do this a little differently. So A applied x1 equals x2, I'm going to subtract and say that's A x1 minus x2 equals 0. And that implies x1 minus x2 equals 0. So all I've done is this basically solve for 0 in my injective statement. Well, what is this saying? This is saying that I have a vector, let's just call it x for the sake of argument, that solves the homogeneous equation. Now, if that happens to be the only one that does it, then I'm injective. So let me say that again. If my only solution to the homogeneous equation is the trivial solution, then my function is injective. This is huge. So what I'm really saying here is all I have to do is take this and look at it in terms of injectivity, or solutions to this. Now, if you think back, what do we learn about fat matrices? This is fat, right? It's wider than it is tall. So A is fat. A fat matrix is always going to have a non-trivial solution. So therefore, Ax equals 0 has a, hit the wrong button, has a non-trivial solution. So I cannot say definitively that x equals 0. It could be some other non-zero vector. And this is me spelling it out for you. Suppose we have a linear transformation with corresponding matrix A. L is injective if and only if Lx equals 0 implies x equals 0. That is my entire discussion on the previous slide. Now, L is surjective if and only if the columns of A span Rm. This is the diamond-crusted theorem from your front of your notebook. And then lastly, L is injective if and only if the columns of A are linearly independent. Now, the columns of A are linearly independent only when you only have a trivial solution to the homogeneous equation. So all three of these make sense when we take L and re-identify it as a matrix. So that's the power of using matrices, is we're going to be able to take something very abstract like a function and characterize it in terms of its matrix and say quite elaborate things about it for instance, injectivity and surjectivity. Here, we're injective if our columns are linearly independent, invoking this. Do the columns of A span R3? This slide. All right, so I have a transformation here given by this. And I really should have some transposes here. I want to prove T is injective but not surjective. Okay, for injectivity, it suffices for me to first view this transformation as a matrix. Well, let's quickly do that. We'll have 3, 5, 1, 1, 7, 3 is our matrix corresponding to T. So I'll just write it as T equals that. All right, we need to determine the null, or how we don't know the null space yet. We need to figure out what the solutions are for Tx equals 0. Well, that means I'm taking 3, 5, 1 and 1, 7, 3 and augmenting it with the 0 matrix. All right. Well, you can see here, will we have any free variables? Well, no, we won't. Why not? Because these two vectors are linearly independent. So that's going back. Why are these columns linearly independent? Well, think back to the lecture series on linear independence. Two vectors are linearly independent as a set if they are not constant multiples of each other. I told you that theorem was going to be important. Are these constant multiples of one another? Nope, they are not. Therefore, we are linearly independent, and therefore, we are injective. All right, now see surjectivity. Well, surjectivity is actually pretty trivial. What dimension space am I staying in? These vectors sit in R3. The greatest number of pivots I could actually achieve from T would be 2. So the greatest number of possible pivots equals 2. How many pivots would I need in order to span all of R3? Well, I'd need 3 pivots. So we're not surjective. And that is in this kind of argument where I look at the columns and see if they're independent, and I look at the number of pivots and see if they're a sufficient number, is typically how you'll prove something's injective or surjective or vice versa, or the opposite of that rather.